Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the online lecture on linear control systems theory. We recently finished our discussion on root locus design, and today we are going to discuss some analysis of control systems with root locus. So this is a usual feedback control system where we have a second order transfer function, and we wish to control this transfer function using some control input. So let's first try to look at the proportional controller. I'm not going to talk about any desirable specifications other than maybe asymptotic stability for this purpose, because the purpose of this lecture is not to teach you the design of the controller, but just to show you how different controllers behave when applied to a system in a feedback control system, in a feedback configuration. So if we use this controller and this is the transfer function, then the open loop transfer function for the root locus would become something like this: kp over s into s minus 1. Notice that this has no zeros, no open loop zeros, and two open loop poles. One of the open loop poles is at s equals 0, and the other open loop pole is at s equal plus 1. So one of the poles is in the right half plane and the other pole is on j omega axis. Let's see what proportional controller can do with this system. So we can sketch the root locus by calculating everything using the 10 rules of root locus. So once we do that and sketch the root locus, then we get something like this. So the pole at plus 1 goes towards the origin, and the pole at the origin goes towards the right side, and these poles meet in the middle at 0.5, and then they break away. One of the pole goes up at 90 degrees and the other one goes down at 90 degrees, as the fourth rule of root locus predicts that whenever the difference is between zeros and poles is 2, there will be two asymptotes, one at plus 90 degree and the other one would be at 270 degree. Okay, so another thing to notice here is that the proportional controller, root locus shows that the proportional controller basically cannot stabilize this system. So whatever gain we choose, there is no gain or no value of the gain where both of the poles come into the open left half plane. So none of the pole actually come into the open left half plane for any value of the gain. So here we can conclude that P controller cannot stabilize this system. So we keep this system and let's try to plug in another controller. Let's try phase lead controller. So you already know that phase lead controller is a controller with one pole and one zero, in such a way that the pole is farther away on the left side compared to the zero. So we have a pole at minus 10 and a 0 at minus 2. That's why this is a phase lead controller, because pole is leading towards the left side. Okay, so once we apply this phase lead controller to the transfer function, then the open loop transfer function that we use to sketch the root locus becomes something like this. So this is the 0 of the controller, this is the pole of the controller, this is the pole of the transfer function, and this is the pole of the transfer function. So overall in the open loop system we have 3 poles and 1 0. So poles are one of the pole is at 0, other pole is at minus 10, and the third pole is at plus 1, and the 0 is at minus 2. So let's see how the root locus looks like with this controller. And once we do all the calculations using the 10 rules of root locus, the root locus turns out to be like this. So this pole at plus 1 and the pole at origin, as they did before, they travel towards each other and break away, but the difference is that here in this case they don't break away right in the middle. So breakaway point has shifted a little bit towards the left due to these pole and zeros. So not only the breakaway point has shifted towards the left, but also after the breakaway, instead of going straight up and straight down, the poles actually move towards the left half plane, and they enter the left half plane with sufficiently large gain. And once they enter, they just straighten up and straighten down after some time. So let's say at minus 3.5 or something. So this would be the point where the asymptotes are join the real axis if they are sketched backward. So asymptote goes up at 90 degree. So this will be the point of the centroid point of root locus. So also this pole travels towards the zero that we have inserted at -2, and this is the pole at -10 which travels towards the 0 at -2 as the gain is increased. So you can see that with the phase lead control, unlike the proportional controller, with the phase lead control we are able to asymptotically stabilize this system, this feedback system, with large enough gain. So when you have zero gain, the poles will be in the right half plane. You increase the gain, this pole reaches here, further increase the gain, and there will be a point where there will be a j omega axis crossing. You can find the point of j omega axis crossing using the 8th rule of root locus. And well, then if you keep on increasing the gain beyond that point, both of these poles enter the left half plane and the system becomes asymptotically stable. And beyond that point, for all the values of gains larger than the value for which j omega crossing occurs, for all the values larger than that, the root locus has asymptotic stability maintained. Okay, so in this case you can see that this time poles do come into the open left half plane, but there is a limit to the transients that can be achieved. For example, you can see that after achieving the asymptotic stability, poles always stay complex conjugate, and we already know that if the poles are complex conjugate, there will be overshoot. That is for the second order system, but we can approximate it for this third order system, because you can see that this is a non-dominant pole. The third pole is not dominant. We have had the discussion of dominant and non-dominant poles in one of the previous lectures. So if we ignore this pole for the time being, then this is a second order system with these two poles, and then we can see that these two poles never come to the real axis, and we might not be, like, for example, if we have a desirable region like this. So if we were to bring the poles in this region, for this type of controller it would be quite difficult, although it might be possible by changing the location of this zero and also changing the location of this pole as well, but the overall shape would remain the same. These poles will always go, one of the poles will always go up and one of the poles will always go down, because the difference between pole and zero does not change by changing the position of the zero and position of the pole. So the asymptotes will always be going plus and minus 90 degrees. So here the poles cannot come in this region. So what do? We shall be trying another controller and see if there is another controller which can bring the poles down in the desired. Alright, so next we try the PD controller, and we place the pole at the same location that we put in case of phase lead controller. The only difference is that PD controller only has a 0 and no pole. So we place the 0 at -2 as we did for the phase lead controller. So the open loop transfer function that for the root locus, that becomes something like this. This is the 0 of the controller, and these are the two poles of the system. And now we sketch the root locus, And now you can see that these two poles, the pole at 0 and the pole at +1, they once again travel towards each other, break away and enter the open left half plane. But this time, since we have added a 0 and no pole, the difference between zeros and poles is 1 and no longer is 2. So these poles do come back and break into the real axis, and one of the pole travels towards the 0 and the other one goes as an asymptote to the infinity. So in this case, you can see that the poles not only come to the open left half plane, but the faster transients can be achieved with less overshoot. So when the pole converges back to the real axis, the overshoot will reduce, and you can see that in this case, this region that we were looking at previously, we can enter the poles we can have the poles enter in this region for large enough gain. But you have to be careful here, because if you increase the gain too much, this pole will go out of this region once again. But then outside the region there is a 0. So once the pole merges into the 0, there is an approximate, not exact but approximate pole 0 cancellation, and still I mean, to keep both the poles within this to the left side of this yellow or orange barrier shape, you have to see what are the ranges of the this gain k. So if you increase this gain k, what will happen is that basically the position of the 0 will remain the same, but the overall closed loop poles will change. So this will become something like, for the gain to be equal to, let's say 10, this will be 10s plus 20, which will get the pole, this 0 will still be at -2. Okay, so let's try another example. And this example, I have a feeling that this example will be really interesting for you. We have a transfer function with 1 0 at -2 and two poles at -1 plus minus j. And if you try with the proportional controller with this transfer function, then what happens is this is the open loop transfer function for root locus, and you can see that here there is no 0 or pole due to the controller. We only have 1 0 and 2 poles for the original transfer function that we had. Okay, so we sketch the root locus of this system, and we can see that we have a 0 at -2 and the poles at +1 plus j, -1 plus j and -1 minus j. So these two poles, what they happen is you can calculate the angle of departure. It would be something like 135 degrees or maybe 120 degrees. But after that there is a break-in point. So these poles will break into the real axis. One of the pole will move towards the 0 and the other pole will go to the infinity. Well, the root locus looks pretty nice. This case, proportional controller is nicely able to asymptotically stabilize the system. Even without any controller, the system, sorry about this, here I also should have changed the transfer function. The transfer function is no longer s into s minus 1. The transfer function is s square plus 2s plus 2. And so this is already asymptotically stable, but adding proportional controller does not destabilize the system, and also gives us a chance to have zero overshoot or reduce the overshoot, because the original system would have at least 5% of overshoot. So if we want to get a 0% overshoot or 2% overshoot, then we can have it. And also if we want to keep the system go like faster, then we can have it. But as good as it looks, there are some limitations with this controller. So suppose we need all the poles to be to the left of the point -9. So -9 is not shown in this graph, but suppose we want to drag both of these poles really to the left. And why would we want to do that? In order to have a very short settling time. So let's suppose we want to have short settling time for this system using some controller, and this diagram shows that for the proportional controller it might not be possible to achieve this objective, that pushing both the poles beyond to the left of the -9 point. So let's see if PD controller can do that. So the same transfer function and the same mistake here. We try the PD controller with we put the 0 of the PD controller really far to the left, hoping that maybe it will shift the center of gravity of the root locus towards the left, and it will shift the overall root locus to the left. And this will be the resulting open loop transfer function that we use to sketch the root locus. Here we have 1 0 due to the system, the other 0 due to the controller, and 2 poles due to the system. And then we sketch the root locus, and to our surprise, the root locus does not move anywhere to the left. The break-in point is still around -3, or maybe it is close to -3. So both the poles break in at -3, which means that although we can drag one of the poles to -20, which is good, but we cannot drag both of the poles to -20. And we want to drag both of the poles to -20, because one of the poles we were able to drag to the -infinity using the proportional controller as well. So in this case, the PD controller does not add any additional advantage compared to the proportional controller. And you can see that if we want to need all the poles to the left of -9 point, then it's not happening with the PD controller. And although already with the PD controller this system is no longer strictly causal, it's hardly just causal. And if we cannot try the PDD controller, because that will make the system non-causal, and we do not deal with non-causal systems, because physical systems are always causal. So we can also try PID, but PID looks to be like a little bit of too complicated at this stage, at least for this type of transfer function. PID, and also we do not need anything regarding the steady state error, but we need the I part because we want to maintain the causality. So in this case, if we introduce the I part, that would be to maintain the causality. But I am tempted to keep things simpler than PID. So what should I do? Did I miss anything? So let's try to think a little bit about. Okay, so sometimes what happens is that in controller design you have to improvise. You have to use your intuition and think about what exactly is our problem. Actually the problem is that there is a 0 at s equal -2, and that 0 is basically not letting the break-in point to go farther than -3. So what can we do about this 0? This 0 does not belong to the controller. This is the 0 of the system. So what we do is that if only this 0 were a little bit farther to the left, but we cannot change the system. So system is the plant. It's something that is given to us. It's something that we are trying to control. It's not something that we can change. So what can we do? We can get rid of so if you remember from the previous lectures, we talked briefly about approximating higher order systems as the second order system, and in that scenario we also talked about pole zero cancellations, and we said that we can do pole zero cancellations only in the left half plane, and luckily this zero is in the open left half plane, so we can get rid of this zero and put a new zero farther to the left using the controller. And how can we do that? Simply by pole zero cancellation. We will put a pole at s equal -2 using this controller. So this is a phase lag controller where we have a pole at -2 and a zero that we put farther away to the left. So we cancelled out the zero that was close to the j omega axis with a pole, and we put a new zero farther to the left, and this makes our open loop transfer function for which we draw the root locus. It has like 2 zeros and 3 poles, but the difference is that 1 zero and 1 pole are exactly at the same location, so they cancel each other's effect. So this system will behave like a system, it will behave like a second order system with 2 poles and 1 zero, and we shall see when we sketch the root locus. And that's the root locus, and you can see that these are the 2 original poles of the system at -1 plus j and -1 minus j, and this is a zero at -2, and it has a pole right in the zero which is cancelling it out. And what is happening is that we put a 1 0 at -20, and that is doing the magic for us. That is bringing these poles farther away to the left, and they are breaking in almost at -40 or maybe -38, and now we can easily achieve our high settling time, low settling time, and fast dynamics with low overshoot, and that would be just like a piece of cake for us now. But it looked very hard in the previous slide when even the PD controller was unable. So sometimes things look tough on the outside, but if you think about them at a deeper level, simple solutions come out. Otherwise you will have to go to the very complex solutions. So this is a simple phase lag controller, but our intuition was the phase lag controller does the job, but the real trick was the pole zero cancellation. So we were not thinking about phase lag controller as such, we were thinking about pole zero cancellation, and it turned out that when we did the pole zero cancellation, the controller that we end up using was the phase lag controller. Okay, so that was that. And next I want to discuss about the effect of adding poles and zeros. We have already talked about the effect of adding poles and zeros previously, but I want to revisit this topic since we have recently discussed the root locus. I want to discuss this topic in the light of root locus. So here is your normal closed loop system. So in this system, if you add any poles or zeros which are outside the loop, so if you add, for some reason there is a system here, some component here which is outside the loop, then this will not affect the root locus. So adding poles and zeros after the loop does not change the root locus of the system, so we don't have to worry about that. But if you add poles and zeros either within the loop, like here or here, so you can think of this as the output disturbance. This is the output disturbance, this is the disturbance which is within the loop. So, and this is maybe sensor noise or transfer function of the sensor. And if you add poles and zeros at these locations in the loop, then the root locus will change, and we shall see how the root locus changes. So if we add we will be discussing the effect of adding poles and zeros, and in our discussion we will assume that poles and zeros are being added in this scenario and not in this scenario. So first of all, we discuss the effect of adding a pole. So effect of adding a pole can be discussed with the help of this asymptote formula. You've already seen this formula, and you already know that when the difference between poles and zeros is 1, then there is only one asymptote, and when the difference between poles and zeros is 2, then there are two asymptotes, and when the difference is 3, then there are three asymptotes. When the difference is 4, there are four asymptotes. So what does this trend tell you? So when the difference was 1, the asymptote was completely to the left, and when the difference increased, now they are neutral. They are neither to the left nor to the right. So you can say they are lesser to the left compared to this scenario. And when you further increase, then it actually bends towards the right. So two of the poles are have the root, the path going to the right side, right half plane. So if you have in this scenario, you cannot afford a very large gain. If you have large enough gain, your poles are bound to cross the j omega axis and go into the right half plane if they are not already in the right half plane. So also in this case as well, poles move towards the right half plane even more quickly. So this 60-degree angle is, this horizontal component is lesser and vertical component is higher. So in this case 45-degree angle, horizontal component is more compared to, so this pole is moving towards the right half plane faster than this pole. So increasing the number of poles overall bends the root locus to the right, and that we already concluded before, but before when we discussed it, it was not with the help of root locus, and now we have seen the same thing with the help of root locus, that adding a pole in general bends the root locus to the right, and which is not a good thing. What happens when we add a zero? So this we can see that in the previous example, in the very first example that we discussed in this lecture, you remember that when there were no zeros in the system, then we had this sort of scenario where the root locus was going not entering the left half plane. But once we added a zero in the left half plane, the root locus kind of bent towards the left half plane, and we were able to achieve the asymptotic stability. So adding a zero in the left half plane bends the root locus towards the left, but not much towards the left, because we also added a pole. So adding a zero and a pole still bends the root locus to the left, but it still keeps this going up and down. So two asymptote scenario is still there. But if we remove the extra pole that we added, we add only the zero, then the bending is more, you can say it is more rigorous, or whatever word you want to use it, that this bending is more compared to this bending, because here we are also decreasing the difference between number of poles. And alright, so in conclusion, we can shift the root locus to the left by adding a zero appropriately. So if we add the zero farther on the left, the root locus will be shifted farther to the left, and so on. So system with zeros in so here just a remark that is a little bit relevant here, but it's outside the scope of our course. That system with zeros in the open right half plane is called non-minimum phase system, and we will not be discussing non-minimum phase systems in this course, but these are the interesting systems. I encourage you to study a little bit about them and think about them as well, because let us suppose we are given a plant that has a zero in the open right half plane, and we already know from root locus rules of the root locus that when you close the loop, the open loop poles converge to the open loop zeros by increasing the gain. And if there is a zero in the open right half plane, one of the poles is bound to converge to that zero. it means that one of the poles is bound to cross over to the right half plane and make the system unstable. So there are some interesting phenomena going on when there are non-minimum phase systems. There are some additional challenges in controller design which are very interesting as well. So this was the discussion about adding a zero to the system, and we have also discussed adding a pole, and that concludes the lecture. And at the end of the lecture I would just briefly go through the whole lecture quickly in a couple of minutes, so you can see that we started our discussion with the analysis of control systems with root locus. We looked at the example with two poles. We tried to apply a proportional controller, could not even stabilize the system. And next we tried the phase lead controller. It was able to stabilize the system, but still there was the relative difference between poles and zeros was still 2. So we could not achieve certain could not bring the poles into certain desirable region. So we tried another controller which was a PD controller, and with that we were easily able to shift the poles into the desirable region. And then we looked at another example which was quite interesting. It was a second order system with a zero. With proportional controller things looked very nice and very good, but just putting a simple constraint of settling time, all the niceness and the easiness of the example went away. And when we tried the PD controller, that's when the real worry came into play, that we cannot even try PDD because that would make the system non-causal. We have to go into PID or maybe PIDD or maybe PIIDD, or I don't know whichever of those controllers. But at this stage I am not willing to make things that much complicated, so I opted to think more deeply about this system and the problems involved in this system. So it turned out that the problem was this zero, and fortunately this zero was in the left half plane. So whenever the zero is in the open left half plane, there are things you can do to that zero, and one of those things is to cancel that zero out. And that's exactly what I did with my phase lag controller, and canceled the zero out. And then very nice root locus where I have poles coming into farther side of the left half plane where I wanted them to be. And that's that. And then we discussed effect of adding poles and zeros, and we saw that how adding poles and zeros affect. Adding poles of course bends the root locus towards the right. We can see that with the help of the asymptotes rule of root locus. And then adding zero basically can bend the pole towards left if the zero is added appropriately. And there is a non-minimum phase system which we have not discussed here, but I have encouraged you to look at it and think about it as well. How would you go about designing the controller when there is a zero in the right half plane, and you know that you cannot increase the gain too much, otherwise one of the poles will jump over to the right half plane and converge to that zero. So with that I conclude this lecture. Thank you for listening. Let me know if you have any questions.